All right, this is question 10. A large sample hypothesis test with the known population standard deviation. This is the population standard deviation. For a null hypothesis, mu is 15 against the alternative hypothesis, mu is not equal to 15, results in a test statistic of z equals 1.37. We actually are using z in this case because we know the population standard deviation. So it's rare, but it does happen every once in a while. But it gives you z. So we're assuming that's known. The corresponding p-value is approximately what? Well, let's roll with what we have. We have a z-score. So we can get a p-value. In this case here, what we're trying to figure out is if a z-score is 1.37. So I guess maybe right about there. And this is a two-sided test. The p-value represents the probability at 1.37, above 1.37. And in this case, because it's two-sided, we also want to know what the probability is below negative 1.37. So what we're going to do is we're going to find this probability, and then we're just going to simply double it. So to find this probability, we're going to use normal CDF, since it's a z. So go to second vars, and we're going to do normal CDF. And our lower bound is going to be 1.37. And this is going above it. So I'm going to do 1E99. Our mean and standard deviation for a z-score are 0 and 1. Oh, let me do that again. And you get about 0.0853. So the probability in this shaded part is 0.0853. Well, this also is going to be 0.0853. You can test that by doing normal CDF and putting negative 1.37 or negative 1.37 as the upper, negative 1E99, but it's the same thing. So what we're going to do is we're going to add those together or just simply double that. So it's going to be about 17% when you double that. And that represents your p-value, the probability of getting a sample that extreme or more, and in this case, both directions, since it's a not equal to. All right, number 11, the t-distribution value for a 90% confidence interval and a sample size of 17. Let me show you two ways to get this. My favorite way of getting the t-distribution critical value is using table B. So I like to use table B on this because most of the time it's just right there in front of your face. You're going to be provided these tables, so you might as well use them. Table B is going to be, you can see that here, we're looking at, in this case here, a sample size of 17. So your degree of freedom is going to be 17 minus 1. And then we're looking at 90% confidence. So if you look at our table, we can go through and we can find 90% confidence. Sorry about that. So we got 90% confidence here, and we have 16 for our degree of freedom. And we're just going to match these up. And it's as simple as that, 1.746. So we'll report that on here as your answer. Now, if you don't have table B in front of you or like to use the calculator, then you're going to go into TCDF, and you're going to enter the following in. Sorry, inverse T. I don't know what I'm thinking here. So your, goodness. Your area is going to be the average of your confidence level in 1. So you just add those together and divide by 2. And your degree of freedom in this case is going to be 17 minus 1, or just 16. So that's how you enter them in there. And you can get the same thing, 1.745 or 1.746 that way too. So I'll let you decide what works for you, but always average that with 1. And then the really if it's 90%, that's really going to be 95%. All right, number 12. Which of the following are characteristics of a t-distribution curve? Answer is 1. The graph of a t-distribution extends infinitely to the left and right. It does that. And approaches the x-axis asymptotically. That just means that it basically gets closer and closer to the x-axis. So t-distributions will look like that. They look a lot like a normal curve. And so as x increases in absolute value. So basically, the further this goes away from the mean, it's going to get closer and closer to x. That is true. There are an infinite number of different t-curves, each determined by a parameter called degrees of freedom. And right there on this formula sheet kind of gives it away, doesn't it, right? These numbers, there's an infinite number between, 1,000 and infinity. Obviously, these numbers are very, very close to each other, but the closer you get to infinity, the more that t-distribution approximates a normal curve. But that is true, right? It'll be more like a normal curve with the higher degree of freedom. The maximum point on the graph of a t-distribution occurs at 0, and they're always going to be centered at 0. So that is also true. Just like a normal distribution, when it's converted to z-scores, is always centered at 0, so is a t-distribution. So all 3 of those are true. And number 13. When performing a test of hypotheses, the decision to choose a z-test or t-test is determined by which of the following questions? Is the sample mean greater than 30? Well, that doesn't guarantee it's going to be a z. Is the standard deviation of the population known? If we know that, that's when we use z. Now, it's a very rare that we know that. So you haven't really had a lesson having to do a problem like that. But if we do know the population standard deviation, we use a z-test. What is the level of significance? That doesn't have anything to do with z or t, but population standard deviation does. So it's going to be 2. And 14, suppose you select a random sample of size phi from a normal distribution with unknown mean and unknown variance, sigma squared. The null hypothesis is mu is 65. To be tested against the alternative hypothesis, mu is not equal to 65 at 5% alpha level. If the resulting sample mean is 68.25, that's your x bar. S squared equals 9. What's the value of the appropriate test statistic and the conclusion? All right, let's stop for a moment here. Here's what we have. We have our null hypothesis. Sorry about that. So we have our null hypothesis at 65, sample mean at 68.25. Now they give us our sample standard deviation squared as 9, but we never use that. We use square root that because we want to know that's really just what s of x is. So if s squared is 9, then s is going to be the square root of 9, which is 3. That's weirdly worded, but anyway, let's go through and just run this test in the calculator. All right, this is going to be a t-test because it's one sample. It's got a sample standard deviation, sample mean. All that's just to say, you're going to do one sample t-test here. We have our stats to enter in. So our stats are going to be for your null hypothesis. We're going to put 65 for that. We're going to put 68.25. We have our sample size of 3, or our sample standard deviation of 3. And it says sample size is 5 right there. So we can put 5 in there. It's a pretty small sample. And our alternative is not equal. So we'll go ahead and select that. And go down and calculate. And here's what we have. We have a test statistic of 2.422. So T equals 2.422. And our p-value is going to be 0.0725. So since our p-value is so large, it's not very large, but 0.0725, it's higher than alpha, so it's greater than 0.05. We're going to reject HO, or fail to reject. All right, I'm just gonna stop writing on this pen here and we'll talk. We're gonna fail to reject HO. That means we do not have convincing evidence to conclude that the alternative is true. The answer choice here is going to be E. Right there, E. All right, I'm gonna stop the video here, figure out my technical issues, and the rest of the problems will be in the last video. Thanks for watching.